Okay, practice problems. Number one, a fire engine is sitting beside the road with its 900 hertz siren on. You drive past the fire engine at 15 meters per second. If the speed of sound in air is 340 meters per second, what frequency do you hear as you go toward the engine? Let's do that one first. So, step number one, we got to figure out which of these three formulas we are going to use. This first formula is for when the source is stationary and the observer is moving. So that's the one we want. So I'm going to write that down. Oh, I think I got that wrong. Yeah, it's not VO, that's just V. So then V plus or minus VO over V. Okay, so now really all we got to do is figure out this first one. It says, what frequency do you hear as you go toward the engine? So go toward. Let's just make sure that we got this right. VO is going to be positive when moving toward the source. So I'm going to change this up. This is going to be just plus VO. And then from now on, it's just, or from here on in, it's just going to be plugging stuff in. So this is the frequency that I'm going to observe. Frequency of the engine was 900 hertz. The speed of sound in air was 340 meters per second. Plus, I'm moving toward the siren at 15 meters per second. That's all over 340 meters per second. And if you plug that in, you get 940 hertz. All right, now number two, the only thing that changes, or I guess that was A and this is B. The only thing that changes is going to be, this will still be 900 hertz. This will still be 340. But now we're going to subtract 15 meters per second. And this becomes 860 hertz. All right, so that's it for that one. Okay, number two. And actually, before I start number two, I just kind of want to talk a little bit about what significance this has with astronomy. This is actually, it's this idea of the Doppler effect that led to the suggestion of the Big Bang Theory. Not the TV show, the actual Big Bang Theory. So what it is that we've realized that from sitting here at Earth, if you look at all the stars that are out there, I did this the wrong color, they're all what's called red shifted. So what that means is that all the stars that we look out in the star or in the sky, they're all more red than they should be. And the stars that are farther away are even more red than they should be. And what that's from is the Doppler effect. So the farther, the faster that these things are moving away from us. So if they're moving, these stars, these more distant ones, are really far away from the Earth. They're moving even faster. So what that kind of shows is that things that are kind of close to us, different galaxies that are close to us, they're moving away from us, but they're not moving away as fast. And the farther out in space we look, everything is moving away from us faster and faster and faster. So the original idea of the Big Bang Theory is that, well, okay, if everything is moving away from us, if you just like rewind the clock, just like turn back time, then at one time, everything was on top of us. Everything was all squashed together. Everything in the universe was all packed into a really tight ball. And that's called the Big Bang Theory, that everything all emerged from a really dense area, if that makes sense. Anyway, yeah, I just thought I just wanted to show you the significance of why the Doppler effect was a big deal. But anyway, we can use this for this type of question too, the same type of thing. So it says a distant star is being observed by an astronomer on Earth. The frequency for sodium light as measured on Earth is 5.17 times 10 to the 14 hertz. The measured frequency for sodium light from the star is actually seen to be 6.10 times 10 to the 14 hertz. See, that's that, more red shifted that I was talking about. It's, it's going to be different, right? if the speed of light is 3 times 10 to the 8 meters per second, what is the speed of the star relative to us? Is it moving toward or away from us? Actually, I shouldn't say red shifted yet. We'll see whether it's red shifted or what's called blue shifted if it was moving toward us. Okay, so we are going to assume that we are the ones standing still and the star is the thing that's either moving away from us or moving toward us. So if you look at your formula sheet, that's going to be this one, right? So it's going to be negative when moving toward the observer, and it's going to be positive when moving away from the observer. So we're going to start off with this formula. Okay, so we're going to start off here. Here's our formula, right? So we want to solve for Vs in the end. We want to figure out what the speed of the star is. And we want to figure out, because it says is it moving toward us or away from us? That's really going to be whether Vs is going to be negative or positive, right? So let's start off by just saying plus. So if we say plus Vs, then what's going to happen is if I solve for Vs, then if I get a negative answer, then I know that this should have been negative. If I get a positive answer, then I know I was right to say positive. So let's start off with positive though and just kind of see what we get when we rearrange. What is happening? Okay. So let's try to get it on its own. So what I'm going to do first is I'm going to divide by Fs so we can get that out of there first. So that cancels and I get Fs. Now I'm left with FO over Fs is equal to V over V plus Vs. All right. Now you might be saying, what the heck am I going to do now? Remember that when I have things like adding in the bottom, think about those as being in brackets. That's really what's being implied. We just kind of get lazy in math and forget the brackets. So what we can do now is actually just move things like we normally would. So just the same way that we've been just moving things diagonally, I can do that with everything in the brackets there too. So let's get this out of the denominator by moving it to the top. So really I'm multiplying both sides by V plus Vs, but just to do things quicker, I'm going to move everything diagonally. So this is going to move up to the left and it's going to be V plus Vs. I'm going to leave it in brackets if you want, just for the visual. And that's going to be equal to, now the FO goes down to the bottom and the FS goes up to the top. So this is going to be V times Fs up top over FO. I'm just going to carry on up here. I want Vs on its own, so I'm going to subtract V from the other side here. So what we end up with is Vs is equal to V times Fs over Fo, and then it's going to be minus V. So that's the rearranged version of this formula. So now we just plug it in. If we get a negative sign, that's going to tell us something. If we get a positive sign, it's going to tell us something. So Vs is going to be equal to, V is 3 times 10 to the 8 meters per second. Fs. So now Fs is going to be the frequency that the sodium light actually should give off. That's what it does give off when it's, if you were to sit right beside that star, that's the frequency it would be giving off. This is the frequency that we are actually measuring. So the frequency of the source is going to be 5.17 times 10 to the 14 hertz. Divided by the frequency that we actually observe here on Earth. 6.10 times 10 to the 14 hertz. And this whole term is going to be, we're going to subtract the speed of light too. So 3 times 10 to the 8 meters per second. Okay, if you do that in your calculator, you get Vs is equal to negative 4.57 times 10 to the 7 meters per second. So the negative is important, right? So let's just kind of look back to our formula sheet. What does it mean if Vs is negative? If Vs is negative, then it's moving toward the observer. So this is going to be 4.57 times 10 to the 7 meters per second toward us. Okay, so that's going to be it that for the practice problems. Go ahead and do your hand-in assignment, and that's going to be our last lesson. So start studying for our final doomsday test.